Hi, in this video I want to talk about describing functions by describing their graphs. In algebra, we often learn about how to describe a function by thinking about when it's positive and negative. So here we're looking at whether a function is above or below the axis. And similarly, we learn in algebra how to find roots and intercepts, places where a function touches one of the axes. So an x-intercept corresponds to a 0 or a root, and a y-intercept corresponds to when x equals 0, what's the y value? In this video we'll focus on the ideas of monotonicity and concavity with their corresponding points of finding maximum and minimum points and points of inflection. In ordinary language we talk about monotone by a voice that never changes. It is always sounding the same. But in mathematics, monotonicity is used to describe whether a function is increasing or decreasing. So a function that steadily increases is monotone, and a function that steadily decreases is monotone. Mathematically, the idea of increasing has a very particular definition. This is the definition. The function f is increasing means that if you were to take any two values in the domain when a is less than b, it is always true that the value of the function at b is greater than the value of the function at a. So here I want to make some comments about the notation. The notation here, f colon d arrow r, which no one would ever read that way, represents the idea that we have a function, its name is f, it has a domain which is a set, and its name here is d, and it sends values, which is what the arrow is for, that d, the domain, are my inputs, going to my outputs, so r represents a target set, and it usually means the real numbers. So f represents the function, d represents the domain, and r represents the target, or the output values. We normally don't let it represent the range because the range is going to be a subset of the target. So for example, I might have a function f that has a domain, the interval from 0 to 1, including the endpoints, and target values that are 0 to infinity, which means that my function is creating positive values. But we don't know that it necessarily reaches all positive values, just that every output is positive. So let's take a look at what this definition means. We're going to imagine that we have a graph, and I'm going to consider particular points. So for example, I might have a point here A and a point B. These are in my domain. Notice that A is less than B. A is less than B. And I'm going to consider the value of my function. So that represents the y-coordinate of my point. So I'm going to have a point at A, and now I'm going to ask the question, if I want to have an increasing function, what does this definition say has to be true about B? Well, the definition says that the value of the function at B needs to be greater than the value of the function at A. So if I were to think, well, where am I at B? I am at this y level, and so the value at b needs to be higher, anywhere above that point. And so now if I consider yet another point, because the definition applies to any two points, here's my point, a new point, maybe it has a name, we'll call it C temporarily, and this point is to the right of both b and a. And so I need to be both above the a level and the b level. Could be anywhere above both those lines. My point has to be above. So as I go to the right, my function has to go up. So my function steadily climbs as I go up. And this is what it means to be increasing. A consequence of this definition can be related to the idea of slope. So for example, if I have 2 points, if I'm increasing, the point on the right has to be above. If I were to think about the line joining any 2 points in an increasing function, so here I have a line joining these 2 points, and I calculate my slope, so I calculate the rise and the run, The definition of increasing says f of b has to be greater than f of a, and so f of b minus f of a, so this is at a, and here we are at b. This is positive, and dividing by b minus a, that's also positive because b is to the right. This value, which is the slope, has to be a positive value. And so the idea of increasing is going to be critically connected to the idea of positive slope. Similarly, we can define a decreasing function. A function f is decreasing. That's a true statement if, when you take any two values in the domain, we'll call them a and b with a less than b, it's always true that the value f of b, which is to the right, is below the value f of a. So let's draw a graph of a decreasing function. We have our axes, and so there's our x and our y-axis. We'll draw our graph. It's decreasing. It's your intuitive idea of decreasing function. And now let's imagine taking any 2 points. Pick 2 points at random. Here's one. Here's another. That means that I've picked a and b. A is to the left of b. And the value of the function f of a and f of b, the value of the function at b is below the value of the function at a. In a similar way to increasing, we can think about this as slope. If I were to join those 2 points with a line and to find the slope of that line, the slope of the line between any 2 points, where b is to the right of a, f of b minus f of a over b minus a, the denominator, because b is to the right, is always positive, but the numerator, because f of b is below f of a, is always negative. And when I calculate that, this tells me that my slope on a decreasing function between any 2 points is always negative. So we've just looked at monotonicity. Monotonicity of a graph describes that it's increasing. As you move to the right, the function goes up. Or decreasing. If you move to the right, the function goes down. A second idea that we need to understand is the idea of concavity. In mathematics, concavity is used to mean that the slope of a graph is either increasing or decreasing. From a practical point of view, we'll see that concavity has to do with how the function curves. A graph is concave up if the slope is increasing, and this is going to correspond to a curve that bends up, so concave up. On the other hand, a graph is concave down if the slope is decreasing, and this corresponds to the natural idea that the curve bends down. In the next few slides, we'll look at what this means from a practical point of view and why it has to do with slope increasing and decreasing. So I introduced the idea that concave up means that my slope is increasing. So I want to talk about now how that relates to this definition. I've given here the definition of an increasing, of a concave up function. And formally it means that if you take any 3 values from the domain and put them in order, so a and b are my edges and c is in the middle, that it's always true that these formulas have an order. And if I look at them, I want to notice that it's a slope. So let's consider our 3 points. We have our point A, we have our point B on the right, and C in the middle. And what it says is if I have my points, the slope from A to C, so here's a point and another point, I can calculate the slope of that segment. Then if I calculate the slope going from C to B, I need to have a steeper slope. So if I were to continue this line out from A to B and continue the slope going on, what we see is my slope from C to B has to be steeper. So I have to be climbing at a steeper rate going from C to B. So my line is a little too steep for my picture. That's a little better. When I get my third point, I need to be somewhere above the line. Now imagine that I consider yet another point, maybe between C and B. So I need to have a slope between C and this point, let's call it D, that's greater than the orange slope and less than the pink slope. And I'm going to have to be somewhere in this range. So let's pick a point. And so now I've got a point that's between those two slopes. So I have a steeper slope than going from A to C, and going now from D to B, I'm steeper again. So what does a typical concave up shape look like? Let's imagine that I have a point, and I'm going to draw a slope segment. And so I now draw another point. My next slope has to be above that line, and so it's going to be a less negative slope. And now I have to be above that line. Oops. And the next slope has to be steeper, so we put in a new point. And then we extend the line so we know what we're comparing to. And the next slope has to be above that line. And so as I continue to increase my slope, the points that I'm creating are creating this upward facing U shape. And so concave up is any shape that has the slope steadily increasing. And you can see that as I go to the right, my slope is going from negative. So here we have steep negative slopes, then less negative slope, less negative, slightly positive, more positive, and my slope continues to get steeper and steeper. And this is what it means to say my slope is increasing. In the same way, concave down describes a function that has a slope that is decreasing. If I take any 3 points in my domain of my function, with a less than c less than b, then the slope on the left compared to the slope on the right, then the slope on the right is less than the slope on the left. So as I go to the right, my slope has to decrease. If I imagine a point and I were to draw a slope that I start with, my new point, as I go to the right, my slope is going to have to decrease. Wrong color. My slope of my next point, as I go to that next point, has to be less than my slope when I started. And now if I continue and find a new point, my slope is decreasing. That slope would then continue. I need to be below that line. So I create a slope. And that slope would then continue. I need to be below that slope. And so as I go to the right, notice that what I'm creating is a shape that's upside down U. It's concave down. And so this is the idea of concave down. It's the slope is decreasing. Most functions we encounter aren't increasing or decreasing. They're somehow a mixture, and they're not concave up and they're not concave down. They're somehow a mixture. So when we want to describe a function, we can't say it's increasing. We can't say it's decreasing because it's not. we can't say it's concave up or concave down because it's a mixture. So what we do is we focus on particular intervals. For example, I might want to focus on this interval going from a point A to a point B. What that means is I'm just looking at the domain as if it was just this little piece. My function, instead of being the whole function, would just be this one little piece. And so, for example, the picture that I've drawn, my function is concave down if I only looked at the interval from A to B. And so we would write that my function is concave down on the interval. If I considered another interval, so for example I might consider points C and D, then what I would now be doing is I'd be restricting my attention to the function going from C to D. And I would ignore everything else about the function. And now if I look at that piece, my function is increasing if I ignore everything else. And so I say that my function f is increasing on the interval. Now if I've included my endpoints when I considered the interval, and the statement is still true, for example, my function is in fact concave down even if I include the endpoints, I can say that it's concave down on the closed interval. And similarly, my function that I've drawn, originally I was thinking about just the points between C and D, but if it's still increasing, including the endpoints, and in my example again it is, then I can in fact include the endpoints. So here's a potential graph. I've graphed a function, I see its picture, and I'm going to now try to just look at it and figure out where it's increasing and decreasing and where it's concave up and concave down. And so I'm going to create some number lines here on my graph. These are going to turn into my monotonicity number line. On this line I'm going to indicate where I'm increasing or decreasing. And for example, if I look at my picture going from left to right, I'm increasing until I reach the maximum. And so this point, which is a maximum, indicates a switching point for, oops, not in the right spot, indicates a switching point for my monotonicity. My function then is decreasing until the point here. So again we have another switching point. It's then increasing as I go back up the function. I have another switching point, and from that point on my function is decreasing. And so I can now describe my monotonicity on these intervals. Approximately, we'll use calculus later to learn exactly how to find these points. It looks like it's about negative 2.25 and 0, and approximately 2.25 for my points. And my function was increasing and then decreasing and then increasing and finally decreasing. And so we would write a sentence something like, my function is, my function is increasing on the interval minus infinity to negative 2.25 and also increasing on 0 to 2.25. And notice that I've used approximate symbols simply to emphasize that we're just estimating based on a picture. We don't know that that's where it's switching. And I'm also including endpoints because in fact if I consider the set that includes the endpoint all the way to the set at the other end, I've obeyed the rule of increasing. As I go to the right, the function does go up, even if I go all the way to the endpoint. Similarly, I can write that the function is decreasing on the approximate intervals negative 2.25 to 0 and 2.25 to infinity. Next, we'll consider concavity. We need a new number line for concavity. And we'll be looking at intervals where I'm concave up and concave down. As I look at my function, always going from left to right, I can see that my function is bending up. And later I can see that it's bending down. So I need to figure out where it makes the transition from bending up to bending down, and it happens to be some point in here where it switches. Now based on the graph it's really hard to tell, but it looks to me like it's about here at negative 3.25 as an approximate value. And so let's mark that down as our point, negative 3.25, as a place where it switches from concave up to concave down. So on the left it's concave up, and then on the right it's concave down. And how far is it concave down? So I'm concave down, and then it's clearly concave up here. There must be a transition point somewhere in the middle. We make our best guess to figure out where, and it looks like it might be here at negative 1. It's a convenient point, so we'll use it, but we don't know. Oh, that's why we're learning calculus. Calculus will give us the tool to be able to find those points. So here at negative 1 and 1, we're making switches, and then by symmetry, it looks like the last switching point should be here at 3.25 approximately. So we'll mark that down as well. And so here we are at negative 1, 1, and 3.25. We call these points where the concavity changes, they're called inflection points. So this is an inflection point. So here we have 4 inflection points. And again, we would describe the function by saying it's concave up on each of the intervals in which it's concave up. So it's concave up from minus infinity to negative 3.25, and again on this interval from negative 1 to 1, we're concave up. It then switches to being concave down from 1 to approximately 3.25, and after 3.25 it switches back to being concave up. And so we can write our sentences. First we say f is concave up on our 3 intervals, negative infinity to our estimated point at negative 3.25, between the points, approximate points negative 1 and 1, and again from our approximate point 3.25 on to infinity. And then we add that the function is concave down on our approximate intervals from negative 3.25 to negative 1, and from 1 to 3.25. Notice that I don't use a union. This is really important. I don't use a union because it's not true that my function is increasing on a union. For example, if I were to say, let's look at the union of negative infinity to negative 2.25, union 0 to 2.25, this function that I would be restricting to is this graph that I've outlined again in red. And notice that my function is not increasing because I could pick a point here on the left and a point here on the right, and my function actually goes down. And so if I think about the union, it's incorrect to say it's increasing. But if I think about each interval separately, it is in fact increasing on those intervals. The last basic skill I want to introduce is the idea of taking the descriptions about the graph and actually creating a graph. So here I have 2 number lines. One represents my monotonicity, and the other number line represents my concavity. And I can use this information to understand basic intervals of particular monotonicity and concavity combined, which means I need to first create a 3rd number line. And what I'll do is I'll mark down all of the points where either the monotonicity or the concavity switches. So at 0, both monotonicity and concavity switch. At 1, concavity switches. At 2, my monotonicity switches. And at 3, my concavity switches again. Now, I now have, let's count how many intervals we have. I've got an interval to the left of 0, a second between 0 and 1, a third, a fourth, and a fifth. I now have 5 intervals, and I can look at each of these intervals and determine a shape. So if I think about the possible combinations, I have increasing or decreasing for my monotonicity, and then I have 2 types of concavity, concave up and concave down. The effect of a concave up shape is that the curve is bent up. So increasing concave up is bent up, and a decreasing concave up shape is also bent up. If I take an increasing function and have it concave down, instead of bending it up, I'm going to bend it down. So I get a basic shape that looks like the top left corner of a circle, and a decreasing concave down shape looks like the top right corner of a circle. So these are my four basic shapes. And if I go look at those number lines, I can determine which of those four shapes to use on each of the intervals. On my first interval, I need to be increasing and concave down, which means I need a shape that's increasing and concave down. On my next interval, I'll be decreasing and concave up. So the shape there is a decreasing concave up shape. Then I'm decreasing and concave down. So decreasing and concave down looks like the third shape. And then I'm increasing and concave down. Which is another shape here. Finally, I'm increasing and concave up, which looks like that. So I now have my basic shapes, and I want to point out a few things. First of all, notice that this point at 0, I'm switching from increasing concave down to decreasing concave up, and this point is going to be a corner. It's impossible to do that smoothly. In a similar way, at the point 2, I'm also not going to be able to do that in a smooth way. I'm going to have another sharp point. So if I go to draw a graph and create my curve, going until 0, my graph needs to be increasing and concave down, at which point it switches suddenly to being decreasing and concave up. So I'm going to have a curve that looks like decreasing concave up until I get to the point 1. We haven't marked any scale, so let's call this 1. That'll be 2, 3, and on. And at this point 1, I need to switch to be decreasing concave down. And so I can now continue until 2. At the point 2, I switch to increasing concave down, and so I'm going to now be increasing concave down, and now I switch to concave up, and so I finish by going to concave up. And so I've got inflection points. Let's see, in each of these points, let's see, this is not an inflection point. I have 3 inflection points. I have an inflection point at 0 where I switch from concave down to concave up, at 1 where I switch from concave up to concave down, and at 3 where I switch from concave down to concave up. I have 2 extreme values. One is here at 0 where I have a maximum, and the other is here at 2 where I have a minimum. So that's how we use the ideas of increasing, decreasing, concave up, and concave down to understand a function.